Cool. So today is going to be, we're going to go over LTE as a protocol, get you guys introduced to how it operates, right? It's going to be more introductory. There's some depth to it, but I wanted to try to keep it approachable. It can feel a bit overwhelming trying to learn LTE, just like it probably was for a lot of people trying to learn Wi-Fi early on. So hopefully we can, my goal today with the LTE overview is really to get it framed up for you so you can understand the terminology, understand the architecture from a high level, and understand how everything integrates together. That way, maybe as you go off after the conference, you have maybe certain areas of interest that you want to dive in deeper on LTE to continue your learning journey on it. And you're able to do that in an effective manner without, you know, a large learning curve. Because for me, at least, the learning curve was just framing the technology up so I understood it and could wrap my arms around it. And then once I understood how things kind of integrated, diving in on individual topics is a lot easier. And then after that, I may or may not, depending on how we're doing on time, give you a brief intro overview of Celona and our solution architecture. Really brief, if anything, not going to go deep on it. Just kind of want to give you a flavor of what an enterprise cellular system looks like. And then we'll do hands-on exercises. We have 40 plus iPhones in the back that are connected to our CBRS private LTE network here at the conference. And we're going to break you out into a couple of groups, do some hands-on exercises with coverage range testing, performance testing, and also some network planning. I don't know if you saw the network planner that I gave a 10 talk on earlier. We'll have you do some exercises in there to get it familiar with how you might start a design. So that's what the agenda is for today. Any questions? I see the first one is with Blake.
Do you have a survey? I was here too, so we wanted to take a look at the survey that box.
So the question is, do I have those survey items, the actual like site survey items? Jamel with IBWave does. It is at the conference. It is not in this room at this time. If someone in the back wants to reach out to Jamel and see if he wants to come in, he's probably in another deep dive though, so. Yeah, so he can show it to you tonight probably. He's got it around. Okay, so let's get started. LTE. Who knows what LTE as an acronym stands for? Raise a hand. Anybody? I'm going to pick you. What does it stand for? Long-term evolution. Yes, that is correct. Okay, we're going to go over some terminology in a little bit, but LTE is the easiest terminology that you can understand because it's very accessible. This is what it's kind of called in the carrier space. Unfortunately, most of the other acronyms are not as well known and are fairly obtuse, to say the least. Just to give you a flavor before we dive into the actual protocol and how it works is, what are some of the highlights if you're just thinking about it from a protocol perspective? Its strengths are here listed up on this slide. Really, it's for predictable performance based on OFDMA, just like you're getting with Wi-Fi 6, but it's mature. It's been around for 10 years plus. So all of the maturity that Wi-Fi 6 is starting down that path with of the code and software base to do OFDMA and do the scheduler and the growing pains that it's going through. LTE has already gone through all that. It's very mature. The scheduler performs very well. And it's a scheduled MAC as well instead of a distributed contention like Wi-Fi. So we'll get into that. It has superior range and coverage, even at similar power levels as Wi-Fi indoors. So from a CBRS spectrum perspective, we'll get into the power limits. We mentioned yesterday that it's 30 dBm indoors. Even with the same power output, LTE has better receive sensitivity and also better ability to keep clients connected at long range. So we'll go into some of that. Like for instance, the receive sensitivity is all the way down to neg 120, neg 125 dBm, and a client can still stay connected. And that's due to how the protocol is implemented. There's some noise floor differences, things like that, but you should know that it has superior range and coverage. Outdoors, up to 50 watts, 47 dBm. So obviously you can get several kilometers worth of coverage out of that if you wanted to. Question?
How is it, like with CBRS being 3.6, 2.4, and 5 gig, how is it that this has better range than
Right.
Wi-Fi? Is it
We're going to get into it. It's based on how the protocol is implemented. So there's some noise floor differences based on the channel width and the resource blocks, and we'll get into that. And then there's also just better receive sensitivity in the chipsets and things like that. I would imagine so. That's probably a Mehmet question. What causes better receive sensitivity in the LTE chipsets?
I mean, it's, well, partly the hardware that goes in there. For example, on the uplink, that becomes very important. The noise figure that you have with the hardware is partly the cost of the RF and the hardware. But the other aspect is you can go to lower data rates in LTE. You can go to hundreds of kilobits per second kind of data rates, so you can operate at much lower SNR values. So that gives you an additional range. And on the uplink also, typically devices go to 24 dBm versus on the Wi-Fi devices typically about 18 and so forth. So there are like multiple reasons that add up to it. Yeah.
Cool, thank you. So for those of you timing, it took me about 6 minutes before I had to go to Mehmet for a question. Some other highlights, seamless mobility. We'll talk about LTE and high-speed mobility. I was actually just talking to Jamel at IBWave today, and he sent me a video of LTE high-speed mobility in a jet aircraft doing 700 kilometers an hour. So when we think, Wi-Fi and mobility and roaming, and that's typically been a pain point in Wi-Fi for a long time, it's a pretty good strength in LTE for high-speed mobility, and those handovers are well coordinated and standardized and supported. Security is pretty good on LTE. It's all SIM-based credentials, so there's no concept of open. I think we covered that yesterday. And then interoperability, it's a global standard. So you take LTE and it works in different bands, obviously worldwide, but it's the same protocol and it's very interoperable anywhere you go. So terminology. Starting from the overall system is typically called an evolved packet system. And what that includes is two main function blocks that I'll say functional areas, and one is the RAN and one is the core. So an evolved packet system is composed of those two items, the RAN and the core. The RAN stands for radio access network, and the core, evolved packet core is the terminology for the core. You may hear evolved packet system, also called system architecture evolution. It's been a running theme in my research and learning about cellular and LTE that everything kind of has more than one acronym for the exact same thing. So just get used to it. You may hear it called one or the other, just know that they mean the exact same thing. For instance, an evolved packet core has many functions within it, but it could also be called an all IP packet network. Means the exact same thing. So if you see those terms, just know they mean the exact same thing. I think this had to do with standards development and the terminology, because originally cellular wasn't IP based. Now with LTE and 4G, it went to an all IP packet network, and then they decided, well, maybe that's a gross term. Let's use something else. I don't know. That's a guess, but it seems to me that's kind of how it seemed to have evolved. And the EPC contains multiple components. We're going to get into those components here in just a second, so you know all the functions that go into a core. The radio access network, long-term evolution, this is how we reference it generically for like cellular, but it actually is very specifically referencing the air interface. So it's LTE is the 4G air interface, and that also has another term that means exactly the same thing, which is Evolved UMTS Terrestrial Radio Access, or EUTRA. And then EUTRA may have an N on the end for network as well. So just know, like, you've got LTE and you've got EUTRA, they mean the exact same thing. That's the air interface. UMTS, for historical purposes, was like the 3G air interface. So when you see evolved UMTS terrestrial radio access for 4G, it's evolving UMTS, and UMTS was the 3G air interface. Moving down into more actual like practical functional things you can get your hands on, and evolved in node B is a base station, is an AP. They all mean the same thing. So when you think, what's my cellular AP? It might be called an E node B. It also might be called a base station. It might also be called, the radios within it might be called a cell. So that's some of the terminology there. A radio can also operates on a carrier, and it has a sector for coverage. So those typically are very closely analogous to the same thing. They might have slightly different implications, but just know a radio operates on a carrier, which is like a channel. And then that radio has an antenna, and that antenna typically is referred to as a sector, and that sector is a coverage area that the antenna covers. And then user equipment, or UE, is a client device. So that's not all of the terminology, but that's the main terminology that you need to know when we go through the rest of this material. Any questions on this before I move on? Okay. Now we get into the good stuff. What's the architecture look like? So this is the components in the EPS. So here we're showing both the RAN and the EPC and functionally how they integrate. So on the left-hand side, you have the UE, or the client device. It would connect to an eNode B. This is the over-the-air, right? This is your client connecting to your radio. The radio then, the eNode B then connects back to the EPC, which is the core. If you're thinking roughly analogous along the lines of Wi-Fi, you could think of the core being analogous, not 100%, but just for framing it up as a wireless controller. So the EPC then has function blocks, and these can be, for instance, in our solution, all in like one package as one appliance or software stack solution, or it could be separate functionally different, implementations of each block. Like in a carrier network, typically they pick the best of breed of each component, and they're separate devices, separate software from separate manufacturers, and they integrate them together through these dotted line interfaces, which are very well defined as well. But for enterprise use case, I think we're seeing most of this stuff be collapsed down into a single solution that you can just buy so that it's simplified and streamlined for enterprise adoption. So the eNode B has two main paths back to the core. The first one is to the MME, or the mobility management entity. This is the control plane. So this is where the eNode B registers to the core. User authentications go through to the MME for authentication. And then the S gateway is the other functional piece that the eNode B connects to. And the serving gateway, or S gateway, is the data plane. So there are tunnels, essentially, between the eNode B to the MME and to the S gateway. And there are multiple tunnels, and we'll get into a little bit of that. Control plane, data plane, makes sense? Okay. The MME on the control plane then has an interface and a connection to what's called a home subscriber server, or an HSS. This is essentially a database of your subscriber information. So think of it analogous to a Radius server. This is where your authentication goes to look up SIM information, subscriber information, and to authenticate those devices onto your network. That's most of the control plane that you need to probably be worried about or understand for this level of depth. On the data plane side, the S gateway is a serving gateway. That's really for within the cellular network. It's the serving for the client. It connects to what's called a packet gateway. And the packet gateway is really like an analogous to a border router. It connects to an external network. And those are typically a packet data network, or a PDN. So from a carrier perspective, when this was all developed, you had a packet gateway that was the gateway by which a client's traffic would get out to an IP network or to an external network, for instance, for internet access. So that functional block was different than the serving gateway, which is kind of within the cellular system operated by the carrier. And it may not have been IP back in the day, but for LTE it is. So you have a serving gateway, you have a packet gateway, the IP packets then go out to an IP network. And if we're talking enterprise network, that would be the integration point for coming out of the system and going into the enterprise network in a VLAN to your, onto your network segments that the traffic would go, then be routed to where it needs to go inside the enterprise to an application or server. Question?
I was just going to ask, see IP a lot here, and then Wi-Fi is layers of integration.
So the question is, there's a lot of IP being referenced. Is there any layer 2 integration with enterprise network, or is it all layer 3? Layer 2 integration as well. So what we'll talk about is, just like you may be familiar with wireless controllers between the eNode B and the EPC, those will be tunnels that can go over layer 2 or the layer 3 routed network. We'll get in the next slide. I'll actually show you what protocols are used and what the tunnels look like. But just know that you plug an eNode B into your network, it goes through your switches at layer 1, layer 2, and you just got to have routing so that those tunnels can get set up back to the packet core. So just like CAPWAP or GRE tunnels, they use their own protocols. It's GTP, we'll get into that in a second, and SCTP. But yeah, they integrate at layer 2 is the short answer. And then outside of your network, coming back out, like upstream from the core to get routed out to a server or something, the enterprise packet core will actually then drop it on a VLAN or something like that. And there's policy that you can configure in there to say these clients go on this VLAN, these ones go on the other one. Very similar to how you do it today. The reason IP is referenced a lot is because historically carrier networks were circuit switched and non-IP based. They moved to IP based. They stress that it's IP based. So all the dotted lines are distinct standardized protocol interfaces between all the functional component blocks. So unlike Wi-Fi world, where you're probably used to very proprietary implementations of AP connects to cloud or to controller and it's their own protocol, and there's no standardization and you can't take an AP and connect it to anybody's controller. Not the case in cellular. All of these interfaces are very well defined and very standardized. And that way you can take, what carriers do is they take these blocks and they purchase different vendors, different manufacturers, and they require them to all have standard interfaces for integration. More than likely from an enterprise scenario, you won't need to know what happens inside an EPC or a core, especially like with the Celona solution. Like all of those functional blocks in the EPC get collapsed down into one deployable component that you just need to know how's traffic get in and out of it. And then all those functional blocks are within the system. But just so you have a frame of reference of what all goes into an EPC. The air interface is LTE UU. This is the air interface, just like Wi-Fi has 802.11. The S1 MME is the connection between the eNode B for control plane. That uses SCTP. The only thing to understand is it doesn't use TCP or UDP. It uses a different IP protocol called SCTP. So that might be a change to support that in an enterprise environment. SCTP can be tunneled over, I believe, UDP in some implementations. So there's some options there. And then you'll see a lot of like S1U, S6A, S11. Essentially, all of those define. So like S6A is between the MME and the HSS for authentication. You're probably familiar with Radius from the wireless world. Very similar to Radius is a protocol called Diameter. That's what is actually functionally used for cellular authentication within the system or to an external system. And GTP-C, let's see, S1U. GTP-U is for the user data plane. That's another big important one to know. So when the eNode B is forwarding user data traffic into the EPC, it's going to have to go across an enterprise network. That's the S1U interface, and that is GTP-U, which is a UDP port. So just know that you need to make sure that that can go through your network. A lot of these here, just for your reference, so you know what protocols might be going through an enterprise network. That if you've got security systems, firewalls, you need to make sure that at least the ones going in and out of the EPC and the eNode B are allowed to traverse that network. The other reason for these functional blocks being still broken out and not collapsed is when you get into situations like intra-carrier roaming or inter-carrier roaming. There's also going to be external tunnels set up, like the S-Gateway will set up a tunnel to a roaming partner to forward the traffic out to another carrier. So when you're doing roaming, there's other interfaces that come out of some functional blocks here for that to happen. LTE is deployed and cellular is deployed in a couple different spectrum bands. Just kind of want to give you, when you hear low band, mid band, high band, a frame of reference of what they technically mean. The definition, especially around mid band, has shifted in the last couple of years based on the FCC trying to reclassify spectrum for 5G. So as of right now, low band is less than or sub 1 gigahertz. Mid band is technically defined as 1 to 24 gigahertz, and high band is greater than 24 gigahertz. So mid-band, they kind of call, the Goldilocks range. It has great coverage and penetration capabilities typically. and good coverage range. So it's kind of where, a lot of carriers look to, it's high value spectrum. And so that's where CBRS sits. It's right in mid-band spectrum. So it's got, decent penetration, decent range, just like Wi-Fi and both bands that Wi-Fi supports today. So 5G, will be deployed in high band millimeter waves, greater than 24 gigahertz. Just know that that's more likely to be very highly attenuated through objects, in-room coverage more than anything. And we can deploy LTE in a couple different fashions. The one that we're going to care about for CBRS is TDD, or time division duplexing, because we're doing uplink and downlink on the same channel, just like you do in Wi-Fi. We have one channel that a radio operates on. Carriers can also deploy their networks if they have paired spectrum in two different bands, or within the same band, I think, actually, too. But they use one frequency for uplink and one frequency for downlink, so they do frequency duplexing that way. TDD, yeah, it's a little bit more complex to implement. It's serial uplink and downlink, so we have to switch between uplink and downlink because we can only do one on the channel at a time out of a given radio. Versus FDD, you could do simultaneous. So obviously if it's on different frequencies, you could have uplink and downlink going at the same time across those different channels. It does require synchronization on TDD, but it works with a single carrier. And that uplink to downlink ratio is configurable. So on an LTE network, since it's all scheduled, right, it's centrally coordinated, I have control as an E node B or as a base station what gets transmitted both uplink and downlink and when. I can have a ratio of how often I'm going to schedule uplink versus downlink. I can weight that uplink to downlink ratio. The importance for that is I can prevent starvation of traffic in one direction versus the other. I can, versus, let's say, if I didn't have control over that, downlink might just starve out uplink or something like that. Here, I can actually determine and weight based on my applications and my environment what ratio I want for uplink and downlink. And it's configurable to a limit. It's not like, I can configure any values I want. There's predefined configuration profiles that you have to select from.
Is it dynamic? Can it react dynamically?
The question is, can it react dynamically to change? No, it's more like a static with some configurability. So you set which frame configuration profile you want, and we'll get into which ones they are, but you kind of set it and leave it.